Good evening, sir.
Good evening. So let's start with discussing few problems. Um, just give me a
So
minute.
sorry, sir, I was late. Yes, sir.
So that is fine. That is fine. Just a second. Okay. So let's discuss a few problems from this assignment two. Last time we have discussed assignment one. Um, and today let us discuss assignment two. So today's assignment is based on a few definitions. Let me write them then as well down. So first we will discuss about the topology. When do we say a collection of subset is a topology? Okay. So last time we have seen a few operations, set theoretic operations on subsets. So this time we will talk about the uh, topology on the collection of subsets. Okay. So first you need to start with a collection of subsets in X. Let's say X is my let's say X is my top. Let's say X is a set. Okay. We say this collection is a topology if the subsets contained inside this collection satisfy a few properties. Topology on X if the arbitrary union, so for u alpha in this collection, okay, where alpha is some index set and this is an arbitrary union, so their union is also contained inside this set. So it is called arbitrary union of sets. Arbitrary union of elements of this collection is also in the collection. Second is finite intersection property. So what does it mean? So if we have a finite collection of a sub collection from this bigger collection of subsets, then their intersection also belongs to the sub collection. Okay. So in other words, the intersection is also a subset in this collection. And the third condition is, yeah, and the third condition is that X, the whole space, an empty set must be elements in C. So these are the so such a collection satisfying property number one, two, three. Okay, is called a topology on X. And moreover, we say X with an acute topology tau on it. We say this tuple a topological space. So whenever I say topological space, that means I have specified a collection, a topology collection on that space. Okay. And yeah, and subsets in this topology, sorry, subsets in this topology are called open subsets of X in X comma tau. So these are the definitions of open sets and this thing. We say we s- say X minus U, which let's say denoted by the complement of X inside the complement of U inside X. Okay, where U is a open set, is closed set in this topological space. Okay, so complement of open sets are called closed sets in the topological space. So I will pause for a second to for you to have a quick look at this definition of topology, and then the definition of the topological space and the open sets and the closed sets.
Okay, sir.
Okay, good. So now the assignment 2 is based on the definition of topological spaces, and then comparison of two topological spaces. Basically, comparison of two topologies on a same space. So yeah, uh, which one is bigger, which one is smaller, which one is finer, which one is coarser, and the discussion of the first week ends on the definition of subspaces, subbases. Okay. So let me start with a few questions from the assignment. So we have this question number one, which says let X be a three element set. Then which of the following collections are topology on X? Okay. First collection is given to be empty set, whole set, singleton A, singleton B, and that's all. The second collection that is given to us, so I will refer them to be tau 1 and tau 2. Second collection is given to be empty set, whole set, A, singleton B, and A comma B. Third set, tau 3 collection is containing B and AC. Collection D has empty whole space X, singleton A, singleton B, singleton C, and that's all. Right. Now we need to check for the. So we have four collections with us. Now we need to check which of the out of these four collections, uh, which collection satisfies the three properties given in the definition of topology. So as you can clearly see, empty set in the whole space is already there in all four collections, all four collections. So property number three is already satisfied, right? We only need to look for property number one and two. Okay. And since the collection is given to be finite many set only, so you just need to look at their finite union, their finite intersection, and that is also quite easy. Now you also notice over here that any intersection with empty set, any intersection uh, of with empty set of any subset S is again going to be empty. Any union with any subset of with empty set is going to be the whole set subset itself. Similarly, any intersection with X of any subset of X is going to be S, and any union of any union of subset with X is going to be X only. Okay. So these are very small observations. So you don't need to worry about you don't need to worry about checking intersection and unions with the empty and X. You only need to worry about the non-trivial elements. Okay. You need to only look for the non-trivial intersection and union in order to check that whether they satisfy property number one and property number two. All right. So now, keeping these observation in mind, I want you to spend some time on this and let me know the answer. And then I will discuss the solutions. Okay.
Sir, option B and D should be the correct one.
Option
D.
B and D should be correct. Okay. This is what you are saying. Okay. May I ask you why D? Why do you think that D will be a topological collection? Topology D.
Sorry, sir. D will not be because if we only take A and B elements, for example, A and B, then intersection of A and B, sorry, union of A and B is not there in E4.
Right. Right.
So
So
D will not
the
be.
same logic that you have reduced that A is not a topological space, you can apply the similar logic over in D as well to say that D is also not a topological space, right?
Yes.
Okay. So D is not a topological space. It's clear to you. Why not C?
Uh, s- um, Sir, C should also be a topological space. Yes, sir.
Okay. So just check for the union. Is the union of
Okay.
these two sides is present in in this collection?
Yes, sir.
Union of
Union AC should be ABC. That is the X. That is the set only.
right, and their intersection is going to be empty. That is also there, right? So
Yes,
it
sir.
is a topological space. That is correct. What about B? B you already said that it's a topological space because their intersection is uh,
Empty.
intersection of A and B is empty. Intersection of A and AB is A, which is already there. Intersection of B and AB is B, which is already there. Union of AB is AB, which is already there. So it is also a topological space. Again, by the similar logic that you gave for D, A is also not the topological space. So these are not topology.
Yes, sir.
Okay. So now what do we have here? So we have two topology on X. Okay. First topology is tau 1 x with tau 2, and the other topology is tau 3. So in other words, we get two topological spaces out of one space. That is what we have, right?
Yes, sir.
So so what I want to emphasize on this is that given a single space, given a single set, you can construct many topological spaces out of that set. Okay, you only need to change the topology uh, collection. Okay, that's all. That's what I want to emphasize on. Okay, good. Now let's move on to another problem. Okay, this is question number 2. Let X be a non-empty set. Which of the following are topologies on X? Option A, tau, which is nothing but the power set of X. We will call it to be tau 1. Option B, tau 2, which is nothing but the subset collection of subsets of X, such that that subset is either X or its complement is countable. Option C, tau 3, which is collection of all singletons from the, yeah, collection of all singletons from the space. Now option D, yes. Now option D, um, right. Option D, which is tau 4, collection of all subsets of U, such that U is either X or complement of U is finite. Okay, so before going to the problem, let me tell what we are doing right now to the new joinee. So we are discussing problems from assignment 2 of week 2 of invitation to topology course. So I have already given the definition. I've already recalled the definition of topology on a given set X. A topology is a collection. A topology is a collection that satisfy these three properties. Okay, topology is a collection of subsets which satisfy these three properties. Okay, so uh, and X with a topology on it is called a topological space, and the elements of a topology is are called open sets, and we define closed sets to be the complement of those open sets. Okay, so this is a quick revise. I have discussed till now one question, and I'm discussing the second question now. Okay, so uh, for those who don't know what is a power set of X, now in this question we need to find out which of the four topology, which of the four collection mm, becomes a topology on X. Okay, so tau 1 is a power set of X. Now for those who don't know what is a power set is a collection of all subsets of X. Okay, for example, if I have this three element set to be X, then its power set is going to be collection of all singletons, collection of all doubletons, and the whole space X an empty set. Okay, so this is a power set of X. So this is the biggest collection you can ever get out of any subset. Okay, so this is the biggest collection you can ever get out of a set, right? Okay, now you guys know the definition of the topology, and you have four topologies with you. Now you need to check for the whether which of the set satisfy the definition. So first I want you to check for C. Is C a topology? I will pause for a minute, and then whenever you have answer for C, we can discuss.
Sir, for C, E3 means we are saying that it is like we are saying that it is a sequence, right?
Right. So Anjali, whatever Anjali said, that's correct. Can you repeat what did you say, Rudra?
That E3 we are considering like a sequence, that is a set of functions.
No, 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 no. There is no function. There is no sequence as well. It is
Okay,
just the collection is indexed by the X itself. So indexing set is X itself. That is just a collection.
okay, sir.
Yeah, collection of all singletons. So as Anjali pointed out, that's correct. That the union of any two subset, any two singletons will not be present in this topology. Okay. So tau 3 is what? Is it is just the singletons. It is just the singletons. Right. So if you take two singletons, let's say X and Y. Okay. So their union must also be present inside the topology T tau 3. But if I do the union, I will get X5, a double term. But tau 3 is only a collection of singletons. So it is not contained inside tau 3. So because of this reason, tau 3 is not a topology on X. All right. And you can also say that singleton is also, sorry, empty set is also not in tau 3. Even the whole space X itself is not in tau 3. Uh, yeah. So there are multiple reasons for tau 3 not to be the topology. Like, for example, empty set is not in tau 3. Similarly, the whole space itself is not in tau 3. So condition 3 itself is not satisfied. So we don't need to look for condition 1 and 2. Okay. Uh, yeah. So it is very not inside. It's very not the topology. Okay. Now let's look at option B. So option A is wrong. Now look at option B. So option B is a collection of subsets where X is either X, the whole space, or its complement is countable. Okay. So now, um, right. So first, let us look at for property number 3. So u is equal to x, that is already there inside tau 2 in the given in the definition itself. What about phi? Does phi belongs to this tau 2?
Yes, sir, because phi will belong to X vacuously.
No, no. Does phi belongs to tau 2? That means does phi satisfy the condition that either it is equal to x or its complement is countable, right? That is why then only phi can belongs to tau 2. It will satisfy the definition of being in the subset, right?
Sir, then no, it does not belong.
Sorry,
Then, sir, it phi won't belong to E2.
pi 1 belong to tau 2. That's what you're saying?
Yes, sir.
Okay. So for pi 1 to belong to tau 2, it is either has to be equal to the empty set or the whole space, uh, or it has to be the complement of x. Complement of x is a empty set, but here we are looking at the complement of phi. So complement of phi is going to be x, right? So complement of phi is what? It is x minus the empty set, which is going to be x only. Now we don't know whether x is countable space or not. It is not given in the question. It is just given to be a non-empty set. Okay, it is not given that whether it is a countable space or not a countable space, right? So this is not true. This is not true that x is not equal to empty set, because x is non-empty. Okay, this is given in the question itself. Now the second option is, the second condition in the definition is that its complement needs to be equal to a countable set, but its complement is nothing but x. Complement of phi is nothing but x. Now the question is x countable? But this information is not given in the question. Okay, so we can't say whether it is a topology or not. Okay, so if x is countable, then only this b makes sense. It doesn't even, I'm not saying that it will be a topology, but since it is given in general, okay, it is given in general perspective, x can be any non-empty set, then you can always take a non-empty set for which you can always take a uncountable non-empty set. Okay, so which will imply that phi empty will set will not be there in this topology. So for example, let me take for example, take x to be r. Okay, so if you take x to be r, the complement of phi will be whole r. Now r is a well-known uncountable set. Okay, r is an uncountable set. So phi will not be, phi will not be in tau 2. Okay, so this option is also not correct. So first of all, is this argument, the argument that I'm giving Is this whether it is clear or not? Good. What about Udra? You? Is it clear to you?
Yes, sir.
Okay, good. That is good. So B is also not a topological space. Now let's come to D. Now D is also similar to the set definition of tau 2, but in place of countable we have a finiteness. Okay. Now again we look for the empty set and whole space containment. Okay, so option D, which says that tau 4 is collection of subsets from X, such that either U is the whole space or its complement is finite, right? Now we first look for the property number 3. So by the definition, X is already in tau 4. Okay. Now what about phi? Does phi belongs to tau 4? So again, for that phi, either phi has to be the whole space or its complement needs to be a finite set, right? But we know by the similar argument that X is non-empty set. So X is not equal to phi is not equal to X. Okay. And if I look at the complement of phi inside X, then it is nothing but, so this is a question mark. So complement of phi inside X is X minus phi, which is X itself. So is X finite? That is also not true, because in this case, again by the similar argument, we are working with the general sets. Our X could be anything. Okay, it need not to be a finite set. So if we start with an infinite set X, then this will not hold. Okay, so if I start with any infinite set, then this tau 4 topology will not be a, this tau 4 collection will not be a topology. Okay, so by the similar reason, phi does not belongs to this for X, for infinite set X, for any infinite set X, right? um, Thus option D is wrong. So this is wrong. So this is also not true. Okay, so is that clear? Was that clear?
Yes, sir.
Good. Okay, now option A is remaining. So what about it? Is A is a collection A, is collection A a topology?
Yes, sir.
Okay, why?
Sir, because the power set of X will contain the element itself and the empty set, as well as all the singletons, doubletons, and all the elements, all the combination of elements. So
Right.
it will.
So if you take any two subsets, so power set contains all the subsets. Now if you take two any two subsets, then their intersection will also be in this power set, right? Because intersection of two subsets is again going to be a subset, and power set is a collection of all subsets. Similarly, if you take any arbitrary union of any subsets, that is again going to be a subset of X. Okay, so by the definition, that arbitrary union will also be contained inside power set. Because of that, tau 1 is a topological space. Okay. Right. Now we so you have now noticed that X with power set is a topological space, and intuitively you must also be able to think that this uh, this topology must be the largest in some sense. Okay, just a second, I got into some problem. Is my screen visible to you guys?
No, sir.
Yeah, I don't know what's. Just give me a few seconds. I need to figure out this thing. What's happening? Um. Okay. Yeah. Okay. So yeah, I was saying about the largeness of this topology. Okay, because why you should intuitively think that it should be the largest topology in some sense. Okay, uh, not even mathematical, but there should be some intuition behind it, because the power set contains any collection you take. Okay, so whatever collection you take, it will be a sub collection of the power set. You should be agreeing on this. So what I'm saying is that any collection of subsets of X is a sub collection of the power set. Okay, right. uh, Sub collection or subset, whatever you may. So in that way, rho X, this power set of X, is should be in some sense larger entity. Okay, and any other collection, whether it is a topology collection or non-topology collection, it should be, it is smaller than this bigger entity. So this gives you some intuitive idea of comparing two topologies, right? So the topology corresponding to this power set should be the largest topology. Okay, and any other topology on X must be contained inside this bigger topology in that way. Okay, so in mathematics we do refer to these comparisons of topology by saying by saying that the larger topology, or the topology that contains the other topology, is the finer topology. Okay, and the smaller topology, which is contained inside a bigger topology, is called the coarser topology. Okay, so finer, so bigger collection So bigger collection is not a mathematical term. Okay, so don't stick to that. It is just for your. I'm just throwing this term for your understanding. Okay, so bigger collection is a finite topology. And whenever I say bigger, smaller, these are all relative terms. Okay, you need to have something in the back of your head to compare it with, right? So these are all referral terms. These are not absolute terms. Okay, so finite topology. Similarly, smaller collection are called coarser topology. And as of you have noticed that the topology given by this power set is a biggest you may think of. Okay, biggest. So in some sense, uh, yeah. So what is on the top? Top is power set. Now, what is on the smallest? What is the smallest topology you can think of? What is the coarsest topology you can think of? So the coarsest topology is this, just collection of uh, the whole space and the empty set. Okay. So first of all, why is this topology? Why is this collection the whole space and the empty set? Just a two set collection. Why is this collection a topology? First of all, that is your question. That should you should ask this question. And the second question is why it is the smallest thing. Why can't anything be smaller than this? This is a topology because X and empty set both are in this, right? Second, if you take union, it is again going to be X. And if you take intersection, it is going to be empty set. Okay, which are also part of this thing. And you can't find any smaller topology because you need at least these two elements. These are the minimal two elements that you require in order to satisfy property number three. So you can't go below this. Okay, you need to have these two subsets at least in your topology. So this topology is called the smallest. Okay, so um, further, if I go for the terminology, then this power set correspond to a topology which is called indiscrete sorry discrete topology, and it is the biggest topology on the space on space. And whenever I say tau, the smallest topology, okay, let me say tau s, so it is the x with tau s is the indiscrete topology. Okay, in uh, yes, right. So in terms of mathematical terminology, this is the finest topology and this is the coarsest topology. Coarsest topology. Okay, so these are the terminology because I think I wanted to shift the uh, theme of the topic to the comparison of topology. That's why I introduce all these things. Okay, any question on this?
No, sir.
Good. Okay, now let me discuss another question, which is on discrete and indiscrete topology, and it is also on basis. So I have not discussed. I have not recalled what basis is. So let me do that quickly as well. collection. So we are assuming that X and tau be a topological space. Okay, we are working with a specific topology, and it is a topological space. X and tau be a topological space. So a collection of open sets. So collection, let's say beta. Okay, collection B of open sets. This um, is called basis of the topological space if it satisfies these two properties. That for a given X element in uh, X and X, there exists uh, a B in your collection B such that X is contained inside that B. Okay. Second is um, union of all these BIs, sorry, union of all these B alphas over this indexing set is the whole space X. So it is a sub collection from the collection of open sets. Okay, it need not to be the whole open set or the whole topology. You are taking a further smaller collection. Okay, so if I can draw a Venn diagram, so so it is like this is your right. So this is your basis, and this whole thing is the topology or collection of, yeah. So the inner circle is the smaller sub collection of the bigger circle, which is the topology. Okay, and this all of this thing is lying inside the row of X. So this is row of X, this is your topology tau, and this is your basis B. Okay, so this is a smaller this thing. Okay, now so let us look at this question number 3 itself. Let X be a non-empty set and beta be a collection of singletons. Just a second. Okay, so there is in the definition of this, there is update. Um, yeah. So whenever, yeah, if X belongs to B, X belongs to B1 and B2, intersection of two for some BI inside your collection, then there exists an element B3 in your collection such that B3 is contained inside B1 and B2. Okay. All right. Um, Now, given this subcollection, okay, given this subcollection of sets, one can generate the topology. Okay, one can generate the topology, which is called topology generated by us basis. So let me write that as well. Okay, so whenever these two condition B satisfy these two condition, the subcollection satisfy this two condition, then we say the topology tau is generated by this beta element. And in terms of this generated set, we can also define the open set, and open as subset. We can also define open set U. So our subset U of X is open if for any X in U there exists element B in your collection such that U such that this B is contained properly inside your U. Okay. So this is the definition of open set in terms of the basis. Okay. So so in the basis collection of bases, you need not to take the open sets. It can be an arbitrary collection, but then it will turn out to be the um, open set. Okay. Yes. Okay. And once you take this collection, satisfying these two conditions, you can talk about the topology generated by these bases, and then you can talk about the open set with respect to this definition of topology. Okay, let me ask you, is there any question on that? Because I have updated this material. twice, so I should ask this, that is there any question as of now?
Yes, sir.
Yeah, please.
Sir, so it is this basis is like similar concept to basis in linear algebra.
No, in some sense, yes, because it generates the whole space. Okay, it spans the whole space. So, like basis, linear spans the whole space, vector space.
Yes,
But
sir.
in this case, also basis spans the whole space, but it is not. um yeah, that's the only similarity. There is no other similarity to the linear algebra basis.
Okay, sir. Sir, and can we have two bases which have no intersection between them? For example, if we have an intersection, then we have found this B3,
Right,
which
right,
can be a proper subset. But
right.
can there be two bases which have no intersection?
Yeah, there can be. There
Okay,
can be
sir.
bases which have no intersection to each other. So it says that whenever an element is sitting in two basis elements, then there will be a smaller basis element which is contained inside the intersection. That is what it says. So if the basis element does not intersect at all, then there is no need to have a third basis element in their intersection, because its intersection is empty. So I will talk about that in this question number 3. That particular
Yes.
example I will talk about in this question number 3. Okay, any other question than that?
Yes, sir. Sir, so the topology space, that is the full space and the null space, that is X and phi. So that will always be the basis. That will always be inside the basis, right?
Yeah, that can be one collection of bases. For a given topological space, you can have more than one number of bases. Basis is not unique. Okay, basis can be
Okay.
anything. Okay.
Okay, sir.
Now the question is whether you want to work with some uh, basis that is useful. For example, if you take x and phi, so x and phi satisfy these two conditions, right?
Yes, sir.
But that basis is not of any use to us. So
Okay, sir.
yeah. So good question. And yeah, there is one more thing. The topology generated by if you take basis to be x and phi, so the topology generated by x and phi will be the indiscrete topology, because topology is what? Topology is the arbitrary union of these things uh, and finite intersection of these bases. So it will be just indiscrete topology. So you won't get the topology, but as of whole. Okay. With that being said, let us look at this question number 3. Now, question 3 says, um, yeah. So where B is the B a basis, right? So topology is generated by basis is. Okay, when I say that topology generated by this, then I define my open sets to be in this way. Whenever I say that beta, satisfy the two condition, then we say the topology generated by, then we define the topology generated by this as follows, as follows, that the open set is going to be a subset of X, such that for any element X in U, there is a basis element for each X in U. There exists a basis element B, such that X is contained inside B and in U. So by this definition, B, this collection of bases uh, are already open set, are all open set. And if I take my basis to be X and phi, as you said, then the topology that I will get will be indiscrete topology. Okay. So yeah. Yes.
Sir, the basis need not be topology space, no?
Basis need not to be the topology space. Basis need not to be the topology itself. That's what you're saying.
Yes, sir.
It need not to be. Yes.
Okay,
It
sir.
can be a smaller collection of that. Yeah. It need not to be. Yes. So I will. So for example, look at this example that I'm just going to talk about, this question itself. So in this question uh, we have given a non-empty set X and a basis. And a basis is nothing but the collection of singletons. Now the topology generated by this B is what? The indiscrete topology, the discrete topology, which is nothing but X with power set of X. Indiscrete topology is consists of phi and X. Okay. Numbers, option C is the finite complement topology, and option D is none of the above. Okay. So we have given a collection of bases. Now we need to look what is the topology generated by these bases, right? So in order to see that topology generated by these bases, one thing you can think of is that you just take any arbitrary union of the basis elements. You take arbitrary union of these basis elements and finite intersection of these basis elements, and what will you get? Okay, that is a one way to look at this. So when you have, that is the hint. And then I will give you some time to think. I will pause for a moment, for a minute, and then I will ask what is your guess. Okay, so the hint is that you need to look at the arbitrary union of this collection B and finite intersection of this collection B, and you need to guess what can you achieve after doing that. Okay. uh, and that will be your topology generated by this space. Okay, so yeah, you can write your answer in the chat box. Okay. So have you? Is there any guess from you guys?
Sir, B.
B. That's good. Yeah, that's correct. Because if you take the singletons and consider their union and their intersection, you will get the whole space of X. You will get whole power set, right? That is correct. Is that clear to you also, Anjali? Okay. Anyways, um,
Sir,
yeah.
what is the finite complement topology?
Okay. Good. So, uh, no, it won't be A, because you are looking for the topology generated by these elements B, right? And whenever I say topology generated by this, I meant this, that I define open set to be this way. But this implies that each of the basis element is a open set. And whenever you have open set, it satisfies the two properties, that arbitrary union is a element in B, is a element in the topology, and their finite intersection is also element in the topology. So you just need to look at the union, arbitrary union of these singletons. So if you do the union of arbitrary union of these singletons, you will get the whole power set. Okay, you can construct any power set. Given any power set can be think of as the union of their singleton elements, right? So in that way you can get any subset of X uh, in the topology, right? And hence the discrete topology will be the answer, because you can, because the topology that you will generate using the singletons will be the power set. Okay, is that, when I say the indiscrete topology only contains whole space X and empty set. Okay, but in this generation, so even this indiscrete topology does not even include the basis B, right? It does not include the basis itself. The singletons are not part of this topology. So this can't be the answer. Okay. And then Rudra asked about the finite complement topology. So let I have discussed this finite complement topology, right? So this option, look at this option D. So this option D is the finite definition of the finite complement topology: collection of all subsets of X where U is either X or their complement is finite. That is the finite complement topology. In this case, you also need to include empty set. Okay, now it is a complete definition. So you say that because that's the problem, right? The complement, that five was not in the in this, five was not there. So that was the problem. So we need to include the that into in your definition. So yeah, this is the definition of finite complement topology. You consider those subsets whose complement is finite set. Okay, those will be your open set. Make sense?
Yes, sir.
Good. Okay. Um, so this is not the answer. This is the answer, and this is also not the answer. Right. And nota is also not the answer. Okay, good. Okay, now let's discuss question number 4. Let X be your natural number set. Then which of the following collections are basis of X? Basis on X. A, all subset where each element of U is even element. Okay. Option B. So let me call them B1, B2, B3. 1, 2, 3, 1, 2, 3 up to n. Option So B2 is the collection of subsets. Okay. Starting from 1 to n, right? And where n is varying. So yeah, that is what the collection is. Where each element of U is a prime element. Option D is um, n plus 1 up to, oh, so and so on. Just keep on going, but it starts at n. Okay. Now, in order to check that whether it is which of the set is a basis, and you need to only check which of them satisfy the condition of being basis. And what were those conditions? So those conditions were these two conditions. Okay. First condition, that for a given x in your space x, there exists an element from your basis such that x is in B. Second is that if x lie inside intersection of two bases, then there has to be a smaller element B3. Okay, so you need to check these four conditions. So I will suggest start with A. So will A be a basis? Right. It does not include the odd numbers. So for a given odd number, you won't find an element in your basis which contains this. So it violates the definition, first condition of the definition, right? So for example, 2, 2, 4, 4, 6, these will be the elements in B1, right? And for 3, you can't find any element in this which contains 3. So B1 is gone. Now, option B. So B1 is not the right answer. Now, option B. Option B, sorry, option B, where the collection B2 is, um, yeah. So B2 is singleton 1, singleton 1, 2, singleton 1, 2, 3, 1, 2, 3, 4, and so forth. This is the collection. Okay. Now you need to say that obviously this satisfies the first condition. For whatever natural number you take, there will be an you can always consider for a given natural number m in natural numbers, 1 2 up to m contains m, right? So first condition is already satisfied. You only need to look for condition number 2. Does condition number 2 satisfies? Condition number 2 says if 2 belongs to two sets 1 2 and 1 2 3, then does there exist an element like singleton 2 or something like that which is contained inside B1 intersection B2? which is contained inside these two intersections. So what is the intersection of these two? Intersection of these two will be
One, two.
2, right? So is there exist an element? Yeah, does there exist an element in B2? Okay, so is there any element which will contained inside B2?
Yes, sir.
Right. What that element be?
Sir, 1, 2 itself.
Right. That is correct. So for given any, uh, because this is these sets are containing each other, right? And we will use this fact to say that. So uh, for example, n is part of, for example, any number is part of all uh, the smallest set that it contains inside is 1 2 up to n, and the biggest any uh, subset that comes after this. Okay, and if you take intersection with that, this set will be at least included in that intersection, and this is a basis element. So this satisfies both of the condition. So it is the answer. So this is the correct answer. Okay, there can be more. Now, so we need to keep on looking for the answer. Now B3 is B3 um, a basis? So B3, what is a subset in B3? Each element of the subset is a prime element. So non-prime elements, by the similar logic given by Anjali for option A, implies here as well. Non-prime elements will not be included in, for a given non-prime element, there won't be any subset in the basis collection um, containing that non-prime element, right? So this will also be wrong. Is that clear? That is exactly the same argument that Anjali gave for option A, except to play, you just need to replace even by prime. So this is a similar argument. Now, what about D? Now, D is interesting. So, what about D?
Sir, it will be basis. It is exactly the reverse of B option.
Exactly. So, for given any element, you will find out. So, given M in natural numbers, there exists this collection, right? Now, um, M is included. Now, for given M in this, what are the possible um, basis element that it can have? So, it can be in 1 to M and so on. It can be 2, 2M and so on and so forth up to you reach M, right, in the beginning. So these M many basis elements it will have. And if you take any two intersection of these two, Bi and Bj, what will have? This intersection will always have this. This intersection will always have Bm sitting inside them, right? Containing the element, containing the element M. So yeah, by the similar logic as you mentioned correctly, um, option D is also true. Good, good. So I hope this is clear to all of you. Good. So you guys only come up with the solutions. I haven't done anything on this. So good. Okay. Now there is one more part. I don't have time to discuss about the comparison. I've briefly discussed the comparison part. If you guys remember. So now I will directly jump on to the questions of subbases, and this will be the last question of today's discussion. Then we will meet next week. Question is, which of the following collection form a subbasis of R? Option A, interval n2 n plus 1. N is an integer. Option B, S1 S2. Open A, close B, intervals in R where B is larger than A and A and B are both rationals. Option C, open interval n to n plus 1 inside R and n is an integer. Option D, S4, close interval A to B in R where A and B are irrationals. Okay. So before going into solving this problem, let me first recall what do we mean by subbasis. Okay. So subbasis S for a topology on X is a collection of subsets whose union is whose union is equal to X. So uh, you only need to check whether their union is equal to whole R or not. That's all. That is what the this question is. Okay. Yeah. So let us first discuss part option A, where we you have given the intervals of integer ending intervals. Now, will their union be equal to the whole R?
Yes, sir.
Right. So this is true. This is trivial. I don't think there is any need for explanation. Similarly, option B. Now B, A is smaller than B, and A and B both are rationals. Right. Now, what happens in this case? If we take the union of this thing, union of these sets, will I get the whole R? Okay, let us first look at option C. So option C, you can option C is open interval n to n plus 1, where endpoints are consecutive integers. So, but those are not included. So integers are not included in this set. So union of these open intervals will be R minus Z. So it is not whole of R. Okay. So it is not whole of R. So that's why it is not a sub basis. So this is wrong. Correct? Option C is incorrect. Now option B, what can you say about option B? So if you take any, yeah, if you take any, um, for example, you can take minus n to uh, n. Okay. Now both of them, okay, you can take n to n plus 1. Okay. In this case, now n is a natural number, so it is a rational also. And if you take the union over n, right? Yeah. So this minus n is smaller than n, right? And both are rationals. So if you consider this union of sets, this is a sub union of this thing, right? And it already includes this is a whole equal to R, because whatever element that you take, uh, if you think that you might miss out, yeah, I don't, you won't miss out of anything in this collection. So this is also a sub basis, right? Are you guys agreeing with it?
Yes, sir.
Okay. So this whatever this example is actually a smaller thing than whatever is given. So this is also um, that. Now, what about if we start with irrationals, and with irrational and irrationals are also included? So this is also, this union will also give you the whole R. Because whatever number you take x, okay, so between two irrationals there exists a rational. So there exists a rationals. Um and if you, so the logic here is that R is nothing but R union R minus, sorry, R is nothing but Q union R minus Q. Okay. R is nothing but union of rationals and irrationals. So if you pick a rational, then there exist two irrationals which bounds that rational. Okay, there is a larger irrational and there is a smaller irrational. So this P will be contained inside A B. And if you take a rational, if you take a irrational, let's say Q R minus Q, then if you take a rational, then you can just consider this interval itself, because it already includes irrational Q in it. So given any element in R, you can that is contained inside the union of these. Uh, yeah. So this union is equal to R. So it is a sub basis. So this is also true. Okay. Any question?
No, sir.
Good. Okay. So we stop here. Uh, Thank you guys for joining, and I hope to see you next week as well. Next week, so I have missed a few things in this assignment, which is the comparison of two topology. So I think I will discuss that in the next session, as well as whatever the material of the next week as well. uh, okay, so see you, take care, and we hope we will meet next week as well.
Yes, sir. Thank you, sir.
Yeah, no problem.